Okay. A very good morning, everyone. I'm Shatanik Bhattacharya, a pass out from Department of Physics, Ramakrishna Mission Residential College, Autonomous Narendrapur, and I'll be hosting this session along with Mr. Olipriya Huri. Hello, hello, am
Yeah,
I
we can
audible?
hear you.
Yeah.
Yes, yes, okay.
So,
Yes,
Go
yes.
on.
Today we have with us Dr. Abhishek Samanta and Dr. Subhankar Khatua, who will be presenting the sessions on their respective topics, which Olimpia will introduce. I would like to call upon Dr. Malay Purkait, the head of the Department of Physics, Ramakrishna Mission Residential College, Narendrapur, to say a few words.
Okay.
Sir?
Thank you. Okay. Thank you, Satani. Good morning, uh, to dear colleagues and guests and my dear students. It is my great pleasure to welcome all the participants today for one day commemorative webinar 2020. We are going to celebrate the Diamond Jubilee of our college. In this occasion, we organized a webinar to change the mind of our students. I welcome the speakers Dr. Abhishek Samanta and Mr. Subhankar Khatua. Dr. Samanta was the undergraduate students of our college during the session 2019-2012. He was awarded the PhD degree on 2020 from Tata Institute of Fundamental Research, Mumbai. At present, he is the postdoctoral fellow at Department of Physics, Technion, Israel Institute of Technology. Another speaker, Mr. Subhankar Khatua, is a senior research fellow, Department of Theoretical Physics, the Institute of Mathematical Sciences. He was also our undergraduate students of our college during the session 2010-2013. This is the first webinar in the history of our college, of our department, which is completely conducted on a digital platform in the line with the social distancing norm due to COVID-19 pandemic. The main theme of this webinar is the challenging of educational dynamics due to the COVID-19 pandemic. I hope that all of you will enjoy the lectures given by our ex-students, Mr. Abhishek Samanta and Subhankar Khatua of our college. We feel very proud for our ex-students. Thanks to all.
Thank you, sir. Hello, I am Olipriya Huri. Without wasting a time, I will jump into the main course of the event. Uh, Before starting, I will just quickly repeat the rules for the participants. Please, if you have any doubt, type it in the chat box. We will surely convey it to the speakers. And another important thing is, after the webinar, you will receive an email from us, and with the filling up the feedback form, you will get the e-certificate from our college. So now I will like to introduce Dr. Abhishek Samanta. He is a BSc student from 2000, passed out in 2012 from our college, and then he did his MSc from IIT Kanpur and PhD from TIFR, and now he is doing his postdoctoral from Israel Institute of Technology in the theoretical condensed matter physics. His topic will be interplay between superconductivity and localization. Sir, Abhishek, Abhishek sir.
Should I start? Or hello?
Hello. We can hear you.
Should I start?
Yeah.
Okay. Hello. Good morning, everyone. Thank you, MT sir, for your kind introduction. So I am delighted and honored to be invited to deliver this talk. Let me start sharing my screen. Just a second. Yeah. So can you see my screen?
Yes, we can.
Okay. Just a second. Okay, so I am going to talk about superconductivity and localization. So this was a part of my PhD thesis. So I decided to talk about this. Now, of course, it's a very broad area of research. But in this talk, I will start from the very basic idea of superconductivity and try to give you also a flavor of my research work as well. So let us first start with the very basic idea of an electrical conductor. So we all know that a conductor is such an object which allows flow of charge or equivalently flow of current in a certain direction. Suppose we have a battery which is connected to a bulb via a wire. Now if the connecting wire is a conductor, then there will be large number of free electrons. Hence, they will flow in a certain direction when they feel the potential difference. So this will create a current flow in the circuit. So here is a cartoon video. So it shows that negatively charged electrons are loosely bound to the positive ion core or nucleus. So when the potential difference is applied, they start moving in a particular direction from negative to positive potential, and which eventually creates a current in the opposite direction. But this is an idealized model in the sense that here we have completely underestimated the effect of temperature. This means that due to temperature, there will be random movements of ions and electrons, and because of that, they will collide with each other and lose energy into thermal energy. So here is another cartoon video, so which shows that the electrons start flowing in a particular direction when the temperature was small, but with increase in temperature, they start colliding with each other, and which eventually prevents the flow of electrons and current drops down to zero. So what we understand from here is that higher the temperature, higher the energy loss, and that will lead to bigger resistance in the system. So the current will essentially drop. So it is expected that with increase in temperature, the resistance will increase in some characteristics way. So here is a plot for resistance versus temperature, and we see that with increase in temperature, resistance also increases. So the question is, what happens when the temperature decreases and it becomes very close to absolute zero value of the temperature? And the answer to that question is that for a normal metal, the resistance decreases and it goes to a value which is constant at t equals to 0. But there are some materials where the resistance drops suddenly to exact zero value beyond a critical temperature. These materials are called superconductors. Now, as you understand that when the resistance drops to zero, the conductivity becomes infinite. Now, this infinite conductivity implies that if a current is passed through the material in its superconducting phase, the current would flow forever without any dissipation, because there is no thermal energy loss in the system. Now, this phenomena of superconductivity is not something very special in some particular material. In fact, this has been found to be a common feature in most of the elements in the periodic table. So here, all the elements which are marked blue or green or yellow in the periodic table, they show superconductivity. So you can say that superconductivity is a common feature of many elements. Now it has several applications. For example, superconductors are used in maglev trains, MRI machine, LHC particle accelerator, fast computing, efficient electricity generation, and many others. Now, the discovery of superconductivity came when Kamerlingh Onnes in 1911 observed that the resistance of solid mercury drops to zero, exactly to zero value, suddenly at a temperature which is 4.2 Kelvin. So all superconductors show this sudden jump in resistance at a particular transition temperature, which is called the superconducting critical temperature, or which is abbreviated as TC. Now, to get a sense of how low this TC is, remember that water boils at 100 degrees centigrade. At 0 degree centigrade, water freezes, and even liquid nitrogen occurs at minus 195 degrees centigrade, and the absolute zero temperature is at minus 273 degrees centigrade. So, for example, here the superconducting critical temperature for liquid helium is at minus 270 degrees centigrade, which is very close to absolute zero temperature. So TC in some of the materials are shown here. You can see that they are very small and close to absolute zero in almost all of the materials what I am showing here. Now the question is, what is the reason behind superconductivity? The first microscopic theory of superconductivity was developed by Bardeen, Cooper and Schiffer in 1957, which is like after 50 years after the discovery of superconductivity. They received Nobel Prize for their theory in 1972. So in this talk, first I will try to explain the basic idea behind the BCS theory, and then I will show how the real systems differ from the assumptions of BCS theory, and so on. So here is the basic idea behind the BCS theory. So we all know that electrons are negatively charged. So if you put two electrons together, they will repel each other. However, sometimes the effective force between two electrons can be attractive also. And that is the main idea behind the BCS theory, that same charge can attract also. So one can visualize this attractive force in the following way. Imagine an electron moving within a material. So the first electron. Now the core of the ions are positively charged. Therefore, the Coulomb attraction between the electron and the positively charged core of the ions will create a distortion in the lattice, which will essentially create an higher positive charge density region. Now, if the second electron comes very fast, then that electron will be attracted towards this higher charge density region. Therefore, we see that because of the first electron, the second electron is effectively attracted. Now, this effective attraction between these two electrons are mediated by lattice distortion or vibration, which are called phonons. So we can say that the weak electron-electron bound pair mediated by phonon interaction is called a Cooper pair. This is the main idea behind the BCS theory, that superconductivity arises when the attractive Cooper pair interaction dominates over the repulsive Coulomb interaction. So here is a cartoon video which shows that when an electron, let me start the video. So it shows that when an electron moves through the lattice, it attracts the positively ion cores, and a region of higher positive charge density is created. So it attracts, so the electron attracts the positive ions, and here the positive charge density increases. Now when the second electron comes, that is attracted towards this region because the positive charge density is large here. So although the same charges repel, here because of this phonon mediated interaction, these two electrons attract each other, and they create a pair, which is called a Cooper pair. Okay. So here here we will study the problem of single Cooper pair using quantum mechanics. So first we write down the Schrodinger's equation for two electrons of the Cooper pair. Now in this equation there are two terms which are the kinetic energy term, which are basically the p square over 2m term, which is written in terms of operators. Now since there are two electrons, so and they sit at location R1 and R2, so there are two kinetic energy contributions from them. Now there is another interaction term U R1 minus R2, and the interaction term depends on the distance between the two electrons, which is R1 minus R2. Now E is the energy and psi is the wave function of the two electrons. Now we will do a change of coordinate, like from R1, R2, we will go to a coordinate system which is dictated by the small r, which is the relative coordinate, which is R1 minus R2, and capital R, which is the center of mass coordinate, R1 plus R2 by 2. So after changing coordinate, the same Schrodinger equation can be rewritten in this simple form. Now notice that in this coordinate U does not depend on capital R. So we can write the wave function in the following way: psi r times e to the I kr, which can be derived also from the Bloch's theorem. Now okay, so now if you put this wave function in the Schrodinger's equation, so we will get this following equation where E tilde is given by E minus h bar square k square over 2m. Now from the expression of E tilde, one can easily see that for a given value of E tilde, the energy E will be minimum when k is 0. So what does it mean? So this means that when the momentum of the center of mass vanishes, means k is equal to 0, so the two electrons of the Cooper pair have opposite momentum, k and minus k. So what we learn from here is that the two electrons in the Cooper pair have opposite spin, up and down, and they have opposite momenta also, like k and minus k. Now since the electrons are fermions, from statistical mechanics, we know that two fermions will form an anti-symmetric wave function, which means that if you exchange between them, you will get a minus sign in front. Now, since the wave function consists of a spatial part and a spin part, the spatial part will be symmetric and the spin part will be anti-symmetric. So here is the full wave function. So the first part is the spatial part and the second part is the spin part, such that the overall wave function is anti-symmetric. Now we put this wave function in the above Schrodinger equation and use the fact that interaction is negative, which is minus u, and it is a constant around the Fermi surface. That is, u is a constant value around within a thin shell around the Fermi surface and 0 elsewhere. And the thickness of the shell is dictated by the Debye energy, which is given by h bar omega d. Now using all of this, we can find that the energy E is given by this 2 epsilon f minus this. Now one can see that this energy is less than 2 times Fermi energy, which means that the initial energy of the Cooper pair was 2 epsilon f, but the final energy is less than that. That means there is a bound state which is formed because of this Cooper pair interaction, which is energetically favorable. Therefore, the binding energy of this Cooper pair is positive. Now, if you plot the binding energy or the excitation energy as a function of the interaction u, you will see that it will smoothly starts from 0. So what I am plotting here is this EB, which is 2 times epsilon f minus E, which is this quantity h bar omega d times exponential of minus 2 over u, and you can see that it smoothly starts from 0. So this means that a bound state can be formed regardless of how small the interaction is. Remember that this bound state is completely different from the free electron case, because in the free electron case there is always a threshold energy to form a bound state. But however, to form a Cooper pair bound state, there is no threshold energy. So the summary is that the Cooper pair bound state is fundamentally different from the free electron case, and the Cooper pair bound state can be formed with any amount of, like any small amount of negative interaction. Now we have so far we have seen that the Fermi C is unstable against the formation of the bound pair. So it will create many Cooper pairs because they are unstable. So far we have studied one single Cooper pair. Now the question is, what happens when there are many Cooper pairs? And the answer is they will condense. Let us see how does that happen. So here is one more cartoon video. So one Cooper pair is formed. Now note that a Cooper pair is a bosonic state. Now bosons can occupy the same state. Since the Cooper pair consists of 2 electrons, now it also behaves like a boson, and many Cooper pairs are formed and they start moving towards the positive terminal of the battery as a huge molecule. So this huge group of Cooper pairs do not feel any resistance while moving, simply because they are very large in size. So this leads to a resistance-less current flow. So remember that whenever something is large and heavy that does not feel any resistance on its path and move freely or smoothly. Here is a video of a rock rolling, and you can see that since the rock is very huge and heavy, it does not feel any resistance on its path and move without any resistance. See the video. So this is similar to what happens in the condensation of Cooper pairs, where large number of Cooper pairs join and move together towards the positive terminal of the battery without feeling any resistance on its path. So the bottom line is that condensation of the Cooper pair lead to a resistance-less current flow in a superconductor. Now to deal with these many Cooper pairs mathematically, single particle quantum mechanics does not work, and we need a better and smarter way to deal with the wave function of the many electrons. So now we need something called many-body quantum mechanics, and the language for this many-body quantum mechanics is the second quantization. So here I briefly introduce the second quantization. So a fermion or an electron is described by 2 operators, C and C dagger, where C is the annihilation operator for the electron and C dagger is the creation operator. For example, in this figure we see that when we apply the operator C on a fermion with a particular spin, then the fermion is annihilated. On the other hand, if we apply C dagger on an empty site, a fermion is created. Now this C and C dagger have 2 indices. So one is site index I and the another is spin index sigma. Now they can be written in real space like this, or they can be Fourier transform to write in momentum space also, like Ck sigma. Now using these operators, we can write the Hamiltonian for the electrons in the following way. The first term is the kinetic energy term, which indicates the annihilating of an electron on site J, which is Cj sigma with a particular spin sigma, and a creation of the same electrons on another site with C dagger I sigma. So this term corresponds to the hopping of an electron from J site to I site, as I am showing in the figure. So that's basically the kinetic energy term, but this term applies only to the electrons which are nearest neighbors. Now the second term is an interaction term, which is the interaction between two electrons on the same side I. Now two electrons with opposite spin sit on the same side, so they will interact via an interaction energy Ui. Now using the second quantum, we can write this operator Ni up, Ni down in the following way. So next, we take the Hamiltonian in terms of C and C dagger and do a Fourier transform to change it to momentum space. So this is the same Hamiltonian, but now rewritten in K space. Now the first term is similar to a tight binding model with the kinetic energy of electrons, with xi k is epsilon k minus mu, and the second term indicates a phonon mediated interaction between the two fermions, which is basically the Cooper pair interaction, many Cooper pair interaction. Now you take, to explain this term, you take two fermions with one with spin up and another with spin down, and they interact via a phonon. Now because of the interaction, the momentum is not conserved, and hence it changes from k prime to k. So in a nutshell, the second term corresponds to the destruction of a Cooper pair at k prime, which is C minus k prime down, C k prime up, and a subsequent creation of a Cooper pair at k, which is C dagger k up, C dagger minus k down. And there is an interaction matrix between them, which is UK k prime. So in a nutshell, this is basically the destruction of a Cooper pair at k prime and a creation at k. Now we see that the interaction term is a 4 fermion term, which has like four objects, C dagger, CC. Therefore, the Hamiltonian is quartic. To make it a quadratic Hamiltonian, we use something called a mean field theory. Now what we do is that in the mean field theory, we write the product of two operators like A and B in the following way, like expectation value of A times operator B plus expectation value of B times operator A minus the product of their expectation values. Now we can apply the same thing here, assuming that this interaction term is also a product of two operators, and we use we give an expectation value to the Cooper pair operator, which is minus U C down C up, and we call it delta. So delta is basically the Cooper pair amplitude, or we can call it superconducting or order parameter. Now using this delta, we can write the mean field Hamiltonian in the following way, like delta times C dagger plus delta star times CC. Now notice, because of this mean field decomposition, the quartic Hamiltonian, which had initially 4 fermion terms, has now reduced to a quadratic Hamiltonian, which has now two operators, C dagger or CC. So now the Hamiltonian can be diagonalized by invoking something called a Bogoliubov transformation. So this Bogoliubov transformation is a canonical transformation which changes this original fermionic operator C to a quasi-particle operator which is called gamma. Because in this quasi-particle operator basis, the Hamiltonian becomes diagonal. So we apply this linear transformation, and so this quadratic Hamiltonian becomes a diagonal quadratic Hamiltonian in this form, Ek gamma dagger gamma, where Ek is the energy. So here we find that the energy is given by square root of xi k square plus delta k square. So here is a plot for E as a function of tight binding parameter xi, and one can clearly see that at xi equals to there is a gap in the spectrum, which is delta. Now in the normal state, when there is no superconducting order parameter delta, we can see that E is proportional to xi k, but due to the presence of the superconducting order parameter, so there is a gap in the spectrum. So we can also call this delta to be a superconducting gap. Now, using all of these above, we can calculate the value of delta, the expectation value of the Cooper pair, or in the other word, the superconducting gap, and it turns out to be this. Now, remember that U originated from the Cooper pair in interaction, which we know that it's a constant around the Fermi surface and its value is negative. Therefore, at this point, we assume that U k k prime is a constant and its sign is negative. So if we use this, then the superconducting gap equation becomes very simple, which is like this, which can be solved easily to calculate the superconducting gap delta T.
You need to unlock your iPad first.
Sorry. So now, here is the plot for superconducting order parameter delta T as a function of temperature T, and we see that at T equals to Tc, the gap goes to 0. Also note that these data points have been obtained from real experiments like indium, tin or lead, and the dotted line is obtained from the BCS theory, and notice that they match quite nicely. So the bottom line is that such a simple theory with lot of assumptions match the experimental data so well. So that's the beauty of the BCS theory, which actually brought a Nobel Prize. So hello. So can you hear me, or are you lost?
No, it's okay. You can continue.
Okay, fine. Okay, so here comes to the next part of my talk, which is the effect of localization on superconductivity, which is more related to my work. Now we can ask how to kill this superconductivity. Now we already have learned that attractive interaction between the Sorry? Is there any question or? Okay, so now we have learned that the attractive interaction between the electrons lead to the formation of Cooper pairs, and which essentially leads to superconductivity. Now the question is how to kill the superconductivity. So a superconducting state is characterized by a complex wave function which is given by delta times e to the I phi, which is basically a wave function of the Cooper pair. Now delta is the superconducting order parameter or superconducting gap, and phi is a phase. Now superconductivity can be killed in two different ways. Firstly, if the amplitude of the wave function goes to 0, which happens in case of conventional BCS superconductor at critical temperature Tc. For example, if you reduce your attractive interaction strength to 0, meaning U to 0, then of course delta will also go to 0. But there is another way where superconductivity can be lost, which is like keeping delta to be finite, but the phase of this wave function is fluctuating. So when the phase is fluctuating, then the phase coherence is lost on a lattice, and then also superconductivity can be destroyed. Now the second scenario can happen if the system has some disorder in it. Now okay, so what do you mean by a disordered system? So in a tight binding Hamiltonian, suppose we add an potential term which is like a random potential, which is Vi times Ni. So that means that, for example, if you consider a square lattice here, then on each side of the square lattice I, there is a random potential which is given by Vi, which takes random values on each side I. Now notice that there is no interaction term in the Hamiltonian, so it's a non-interacting problem which can be solved easily. Now since the potential is random, the electron will always try to sit on the sites where the potential energy is small, and the wave function will be localized around that particular site. Look at this figure. So here the potential energy is small on these two sides, and the particles also try to sit here and therefore the single particle eigenstates get localized around that. So this incidence is called a single particle localization or Anderson localization, which is discovered by Anderson in 1958. And because of this localization, the electron stops moving within a lattice, and it actually creates a insulator, which is called the Anderson insulator. Now we will try to see the effect of this disorder potential VINI on superconductivity. So what we do is that we add this random potential on the Hubbard model. So the same model which I discussed earlier, but now I have another term which is a random potential term, VINI. So the first term is the hopping term, which is the kinetic energy term, like when a fermion hops from one side to its nearest neighbor side. So there is a cost of energy which is given by T. The last term is the Cooper pair interaction term with a minus U interaction, and the intermediate term is a random potential which takes random value on each side. Now here again we will play the same strategy, like we will do a mean field decomposition of the interaction term, but now since there is a disorder potential, so we cannot go to the momentum space, and we have to solve the problem in real space. So that's a much more difficult problem than the earlier case, which is called the inhomogeneous mean field theory or Bogoliubov-Dijen's mean field theory. So here we put two mean field parameter, delta I, which is the superconducting order parameter, but now delta depends on each site because of the random potential, and also there is a local density term which is Ni, which is the density on each site. Now using this mean field decomposition, we can write the mean field Hamiltonian, and we can solve and calculate the mean field parameters in the same way. And here is the plot for the superconducting order parameter delta I. Notice that the superconducting order parameter delta I depends on site index I. That's why I have plotted on a real lattice, which is like a 24 cross 24 lattice, and on each side of the lattice I there is a particular value of local superconducting order delta I. So in the clean limit, when V is very small, like for example when V is 1, you can see that there is not much variation of color, which means that the value of delta is more or less constant on the lattice, which is the BCS limit. Because we know that in the BCS limit, which is the clean limit, superconducting order parameter has a constant value, and which is also seen from here. Now now when you start increasing the disorder value, for example from V equals to 1 to V equals to 3, we see that the delta starts becoming non-uniform, meaning it has some value which is large, which is given by red, and there are some value which is blue, which is small. Now in the limit of very strong disorder, for example when V equals to 6, delta forms a patchy structure, which means that there are some particular regions where we can see that delta has a very large value, and most of the regions the value is small. So it is said in the following way, that it forms some good superconducting regions which are marked by this red or yellow, and these good superconducting regions are separated from each other by some insulating regions or non-superconducting regions. So now next we plot the average value of this local superconducting order parameter or delta I. So now we will plot the average value of this. So here we plotted delta I. Now we plot the average value of delta I, which is called delta OP, which is the order parameter, and we also plot the fermionic excitation gap, which is the E gap, which is like the lowest positive energy in the spectrum. Now remember that in the BCS limit or in the clean limit, this delta OP, which is the superconducting order parameter, and E gap, which is the superconducting order parameter, they were actually same in the clean limit, which is also seen from here, that when V equals to 0, delta OP and E gap, they are exactly same, which we also explained in the BCS theory. But here, in presence of random potential, with increase in V, one can see that they start behaving differently. For example, with increase in V, the superconducting order parameter delta OP, it monotonically decreases and it's going towards 0 value. But the E gap, which is the fermionic excitation gap or the superconducting gap, that remains finite even in presence of very strong disorder. Now here is an experimental data of phase diagram of strongly disordered niobium nitride sample. So here two temperature scales have been plotted, T star and Tc. Now T star is the temperature at which the superconducting gap goes to 0, which is this E gap goes to 0. And Tc is the temperature at which superconductivity goes to 0, which means the delta goes to 0. And they have been plotted as a function of mean free path. Now notice that mean free path and disorder are inversely proportional, meaning when you have a large disorder, mean free path is very small. So when I am talking about small disorder here, that corresponds to very large value of L or very large value of mean free path here. So now you can compare these two plots, that in the clean limit we saw that these two energy scales like delta OP and E gap, they were same. Here also we can see that T star and Tc are same, and with decrease in mean free path, which means that increasing in disorder strength, T star, which is given by this red region, so they remain finite, but the Tc, which is the superconducting critical temperature, that monotonically goes towards 0. So this is a real like experimental data. So we notice that there is again an excellent match with the experiment from the theory. Now, so we have already explained that in presence of disorder, the superconducting order parameter delta OP and the superconducting gap, they are not same, they behave differently. And we have found that in presence of strong disorder, the superconducting gap remains finite. So which means that the single particle excitation gap remains finite. So but we are interested in low energy excitation of the system, which means that we need to go to the higher order, which means we need to study the two particle excitation, because single particle excitation gap, which is the Cooper pair gap, which is finite. So we will go to the two particle excitation, which is called the collective mode excitation. So here is the part which I have worked on. So so now going beyond the mean field theory, we have added spatio-temporal fluctuation of the superconducting order parameter. So meaning, so we started with a mean field value of delta I, which is the local superconducting order parameter. So now we are going to the higher order, like we are adding amplitude and phase fluctuation on top of that. So now the new delta is given by delta naught I plus eta times e to the I theta, where eta is the amplitude fluctuation of the superconducting order parameter and theta is the phase fluctuation of the superconducting order parameter. Now we use an action-based functional integral formalism, and using the field theory description, we write down the Gaussian action corresponding to the amplitude and phase fluctuation around this mean field value delta naught I.
Abhishek,
yes.
Abhishek, just 1 minute. Please wait for 1 minute, because our participants are not able to see the chat box. So they will have to refresh their chat box. The participants বলছি যারা শুনছো বা শুনছেন তারা কাইন্ডলি চ্যাট বক্সটা একটু রিফ্রেশ করে নিন, তা নাহলে দেখতে পাবেন না। আবার বলছি স্পিকারকে একটু ওয়েট করতে বলেছি, জাস্ট এ মিনিট। তো এর মধ্যে আপনারা বা তোমরা যারা দেখছো চ্যাট বক্সটা একটু রিফ্রেশ করে নাও, যাতে তোমরা চ্যাট বক্সে দেখতে পাবে মেসেজগুলো বা লিখতেও পারবে। ওকে, অভিষেক কন্টিনিউ।
Okay,
Thank you.
let me continue. Okay, so here we have added the amplitude and phase fluctuation of the superconducting order parameter delta naught I. So eta is the amplitude fluctuation and theta is the phase fluctuation. And we have written down the Gaussian action corresponding to the amplitude and phase fluctuation around the mean field value. And we essentially calculate something called a two-particle spectral function, which is the correlator between this delta and delta star. The important thing is that, so this quantity, which is called a two-particle spectral function, this is measurable quantity in a Josephson spectroscopy experiment. So now here we will present the data in presence of strong disorder, which is like V equals to 6, and for a particular disorder configuration. Now, from the mean field calculation, we have already seen that in presence of very strong disorder, the superconducting order parameter delta 0, it becomes patchy, which means that it forms some good superconducting islands, and they are separated from each other by some non-superconducting regions. However, this quantity delta naught is not a good experimental observable. So we cannot do a real life experiment to measure these values. So we need something else. So next we plot the two-particle spectral function, which I already explained that it is a measurable quantity in Josephson spectroscopy experiment. And then we plot the local superconducting gap, which is a measurable quantity in STM. So the plot B and C, they are actually measurable in experiment. Now we see, now what we do is that, so we make a contour according to the good superconducting islands here, and we put the same contour in other two plots, and we find that there is a correlation, strong correlation between A and B, meaning there is a correlation between superconducting order parameter and this two-particle spectral function, which is a measurable quantity in Josephson spectroscopy. And we also found that there is a strong anti-correlation between the superconducting order parameter and local superconducting gap. Now remember that I have already explained that in presence of strong disorder, the superconducting gap, this and the superconducting order parameter, they are not same. And here we find that they are actually anti-correlated. They are completely opposite. So the key finding from here is that we find two experimental observable, namely the two-particle spectral function and the local single particle gap, and there is a strong anti-correlation between them, so which can be experimentally observed. Now, to quantify this anti-correlation, we calculate something called a covariance between these two experimental measurable quantity, and we plot it as a function of disorder strength V. So obviously in the limit of clean case, they were same. That's why they do not have any anti-correlation. But with increase in disorder strength, they become more and more anti-correlated, and the covariance, meaning the negative covariance, increases with increase in disorder strength. Now we will study the two-particle spectral function, which is a measurable quantity in Josephson spectroscopy in Q omega space. So here I will discuss the contribution to the two-particle spectral function from the amplitude. Now with increase in disorder strength, this Higgs mode gets broadened in width and it comes down towards the lower energy also. And at a sufficiently strong value of the disorder, the initial collective mode structure is completely lost and it is mainly governed by the Higgs mode. Now from here we can define something called a Higgs gap. The threshold energy at Q equals to 0, where the Higgs mode appears. And here we plot the Higgs gap as a function of disorder strength V, which is marked in brown, and you can see that the Higgs gap monotonically decreases with increase in disorder strength, and it goes towards 0 at a value of V equals to 5. So next we look at the phase fluctuation contribution to the two particle spectral function, and we make the similar plots, but these plots are qualitatively different from the amplitude part. There is no flat Higgs mode, but there is something called a Goldstone mode at small q. So you can see that there is a very strong linear region here, which is called the Goldstone mode, which remains with increase in disorder also. Now from the slope of the Goldstone mode, we can calculate the velocity of phase velocity, and here we plot the phase velocity Cs as a function of disorder strength, and we can also see that monotonically goes down and becomes 0 at a critical value of the disorder, which is again something close to 5. So this indicates that there is a possibility of superconductor insulator transition at this critical value of the disorder, where both this Higgs gap and the phase velocity go to 0. Now there is a question whether this Higgs mode, which is very interesting in condensed matter physics, can be observed in experiment, or it will always be dominated by the phase fluctuation. Because when I showed the plots, you can see that the phase fluctuation were very strong in magnitude. For example, if you take this plot, which is at v equals to 1, the phase fluctuation magnitude is going from 0 to 10, where the Higgs fluctuation going from 0 to 1.5. So the phase fluctuation is dominating. So the question is whether there is a way to observe this Higgs mode, which appears in the amplitude channel. Now to answer this, now it's a long-standing question in condensed matter physics, whether this disorder-induced Higgs mode can be observed in experiment or not. So here we will try to answer that question in the following way. So here we focus on the q equals to 0 mode of the resultant spectral function. So instead of looking like full q omega spectrum, we only look at the q equals to 0 mode. Now here the black curve is actually the spectral function. You can see, and I have plotted this P11 and P22 are the amplitude or the Higgs and the phase contribution, and one can clearly see that in the low energy limit, like when omega is small, the black curve is like it is mainly getting the contribution from the red curve, meaning it is dominated by the phase fluctuation. But at a sufficiently like large value of energy, which is also somewhere in between, the curve is dominated by the phase by the amplitude fluctuation or the Higgs fluctuation. So the conclusion from here is that so the spectral function is dominated by the phase fluctuation at low energy, but the Higgs contribution comes at a finite energy, which is spatially well separated from the low energy phase pileup. So Higgs is spectrally separated from the phase pileup for small q values in an energy resolved way, meaning if you plot it as a function of energy, you will see this Higgs mode separately from this large phase divergence. So it can be actually experimentally measured in an energy resolved way. So here is the summary of my talk. So in the first part, I showed that when the two electrons attract each other, they form a bound state called Cooper pair, and the condensation of the Cooper pairs lead to superconductivity. Now BCS theory is a mean field theory which can explain the superconductivity in a clean system. Now disorder leads to localization and Anderson insulator. Then we have studied the effect of disorder on superconductivity using inhomogeneous mean field theory. We have shown that in presence of strong disorder, some good superconducting islands are formed which are separated from each other by insulating regions. We also showed that in presence of strong disorder, superconducting order parameter and superconducting gaps are not same, unlike the BCS case. So then we have added the amplitude and phase fluctuation of the local superconducting order parameter, and we derived the fluctuation propagators using an action-based field theory. Then we showed that the local gap and the spectral function are anti-correlated, and hence they can be tested experimentally. And then finally we showed that Q is equal to 0 Higgs mode of the spectral function. It shows the Higgs mode separately from the phase divergence, and hence it can be observed experimentally. So here I acknowledge my collaborators, and here is the work we have published on this. So thank you.
Thank you, Abhishek.
Yeah.
There are some questions in the YouTube. We will take the YouTube questions first, and then
Okay.
sir, please explain the basics of BCS theory again.
Can you repeat the question?
Please explain the basics of BCS theory again.
Okay. So the basics of the BCS theory is that the two, like whenever you have an attractive interaction between two electrons, they can form a bound state, which is called a Cooper pair. And when there are many Cooper pairs like this, like they behave like bosons, and they can go to like the same state, and they move toward the positive terminal of the battery together, and this actually creates a resistance-less flow, which is basically the superconductivity. That's like in a nutshell.
Okay, thank you. Another question is superconductivity is possible in room temperature?
Yes, it is possible. In this talk, I am not going into that part, but I think no, sorry, like the question is like I answered it wrong. Like there are something called high temperature superconductors, but not at room temperature. Like the high temperature meaning that, for example, here you can see that TC is that 92 Kelvin or 30 Kelvin, but room temperature superconductors have not been found yet.
Okay,
but there are high temperature superconductors.
Okay, thank you. So, are there any other questions from YouTube or teachers? You can unmute yourself and ask him.
Okay.
Hi, I have few questions. Can you hear me? Okay.
Yeah, I can hear you.
I thought the chat box was visible to everybody, but anyway.
Yeah.
So the first question was when you did the mean field decomposition
Yes.
in the BCS theory. So like, why that particular decomposition? I didn't understand that part.
Because we already knew that there is something called a Cooper pair, and that pairs between opposite spins and opposite momenta. So that's why like we took this particular combination to be one mean field parameter. Like we had some earlier like intuition about this.
I see.
It's not ad hoc.
I see. Okay. So if we assume something else, let's say k with k prime, how that?
Yeah, you can try that, but you can show that their magnitudes will be much smaller than like compared to this. Like this is the dominant contribution. You can of course like try that.
Okay.
That's the like decomposition. Yes.
I see. So I have a couple more questions.
Yes.
So I'll ask it here, or maybe somebody else should ask, and I'll ask later. I don't know.
No, you can ask.
You can ask.
Oh, thank you. So and then you have discussed about this random potential in the lattice.
Yes.
So what is the origin of this random kind of potential in the lattice?
So like origin of the random potential is like on a like real lattice or in a material. Like there are some like for example some broken bonds or like some impurity, like potential. Like you can never find a clean system. Like there are always some kind of impurity, like on your system. When you try to do some like experiment, you will always find some kind of impurity on your lattice, like dangling bonds or broken bonds, or yeah, something like that.
Yeah, so
Some charge trap. Yeah.
So there are impurities, but it's totally random. Is that observed in experiments? Actually,
Yes.
so my question is about the randomness.
Yeah. Yes. Because there is no other way to like model that, because they come randomly. Like you don't know like on which particular bond there can be an impurity. That's not like possible to know.
Okay. Thank you. And the last question is, so you have shown these plots where the superconducting patches are forming.
Yes.
So there
I think,
you are
yeah.
varying the strength of the disorder, and then you are getting patches, right?
Yes.
So, like, what is the role of temperature here? Like, is there any TC or?
So here we have this data is actually at zero temperature. Like the assumption is at zero temperature, exactly at zero temperature.
Okay. Thank you.
Okay.
Hello, Abhishek da.
Yeah.
Another question is, in the BCS theory, the Cooper pairs which are effectively boson form a BEC, Bose-Einstein
Yes.
condensed state, that is K equals to zero mode. That is with
Yes.
the collective zero momentum. So how
Right.
can they make movement to make resistance zero?
Because their momentum is zero, but their charge is not zero. Like so, no. So this K is actually the center of mass momentum. Do you understand that? So what I mean is that the total momentum is not zero. The momentum compared to their center of mass, relative to their center of mass, that is zero.
Okay. Another question is, why Cooper pair follow Bose-Einstein statistics?
Because their spin is zero. Like total spin is zero.
Okay.
Because boson can follow these like integer number of spins, and fermions are with half integer spins.
Yes.
So electrons are fermions and bosons are Cooper pairs.
Can I break the Cooper pair? If possible, what's the order of energy?
That's actually a very good question. So that's essentially saying that how to, for example, here also, when you are increase your disorder strength very large, you can see that delta is going towards zero. That means essentially you are breaking the Cooper pairs. Like delta is the amplitude of this particular coupling, C up, C down, and when it is going to zero, that means you are actually breaking them. Now the order of energy, I can tell you the answer like from the theoretical calculation, but I don't have much idea like at this moment about the real energy scale in experiment. For example, here for an interaction strength U over T is 3, you need a like random potential of the order of 6 or 7, maybe 7 to make this delta to zero.
Okay, thank you. That's all, I guess.
Is there any other question? Or
no, I guess.
you said, do you have any question? Sorry, we can't hear you.
You are muted.
শোনা যাচ্ছে না এমপি স্যার?
অভিষেক
হ্যাঁ,
সুপার কন্ডাক্টিভিটি ভুলেই গেছি, বুঝেছো?
বোঝা গেছে কিছু?
হ্যাঁ, প্রথম দিকটা আমার ভালো লেগেছে, ভেরি নাইস, কিন্তু শেষের দিকেই সব ভুলে গেছি।
অ্যাকচুয়ালি আমার এই অবধি বলতেই হতো আর কি কিছু জিনিসপত্র, বাট
প্রথম দিকটা ভীষণ ভালো লাগছিল, ঠিক আছে, তারপরে তো আমি ভুলেই গেছি সব জিনিস। ভেরি গুড, নাইস। ওকে,
থ্যাংক ইউ।
দিদি স্যার আপনার কোনো কোয়েশ্চেন আছে?
আমার প্রশ্ন হচ্ছে নেই, আমার হচ্ছে এমপি স্যারের মতোই প্রথম দিকটা ভালো লাগলো খুবই, পরের দিকে ট্যান হলো। আর প্রথম দিকে যখন ভালো লাগছিল তখন ওই কুপার পেয়ার শুনে মনে পড়লো মাস্টার ডিগ্রিতে আমাদের বন্ধুদের খেপানো হতো কুপার পেয়ার বলে। মানে তখন অতটা বুঝতাম না, কিন্তু ওই যারা সলিড স্টেট স্পেশাল পড়তো তারা ওই ওয়ার্ডটা খুব ইউজ করতো। তো এখন এটুকু আমি বুঝেছি যে কুপার পেয়ার জিনিসটা কি, কিভাবে ইন্টারঅ্যাক্ট করে, মানে তোমার লেকচার থেকে ওইটুকু মানে আমার নলেজ আজকে বাড়লো যে কুপার পেয়ার জিনিসটা কি, কিভাবে ইন্টারঅ্যাক্ট করে, এবং ওরা যে বোসন হিসাবে কিভাবে ইন্টারঅ্যাক্ট করছে, সেগুলো প্রথম দিকে ভালোই মানে মনে হয় ঠিকঠাক বুঝেছি, তারপরে ডেফিনেটলি আমার মানে রেঞ্জের বাইরে চলে গেছে।
বিশেষ করে দিদি স্যার, বিশেষ করে ওই যে ছবিটা, মানে যখন ইলেকট্রনটা মুভ করছে, এটা দেখেই যে ডিস্টরশন সলিড ক্রিস্টালের মধ্যে, আয়ন ট্র্যাপের মধ্যে, আয়নগুলোর মধ্যে, সেইটা কিন্তু ভালো লাগলো। ওটা দেখেই একটু বোঝা গেল যে একটু অনেকটা ক্লিয়ার হয়েছে।
এক্স্যাক্টলি, ওভারঅল ভালো হয়েছে, তোমার লেকচার ভালো হয়েছে, অনেকটা কভার করেছো, মেটেরিয়ালস অনেকটাই কভার করেছো। আর আমাদের স্টুডেন্টসরা তো এখন পড়াশোনা করছে, ধরো সুপার কন্ডাক্টিভিটি মাস্টার্স লেভেলের স্টুডেন্টসরা তো করছে।
সবটা তো বোঝার কথা নয়, বাট আমি চেষ্টা করলাম সেকেন্ড কোয়ান্টাইজেশন একটু করে বলতে কিভাবে হয় কি না।
ওকে, ভেরি গুড।
ওকে, থ্যাংক ইউ।
ওকে, থ্যাংক ইউ।
Abhishek da, hello.
Yes.
Yeah, I had one question. So, how is Josephson spectroscopy, as you mentioned earlier, used in the study? I mean, how is it exactly used? Any idea?
That's a difficult question to answer here. So what is done is something like, if you have two Cooper pairs, like for example, you can remember that I calculated something called a two particle spectral function, which is the like correlator between two delta. Like suppose you have two Cooper pairs, and if there is a tunneling between them, then Josephson spectroscopy can capture this amplitude.
Okay.
That's all I can I think I can say right now, but yeah.
Okay, thank you.
Okay.
Okay, thank you, Abhishek. So we should proceed, MP sir,
To the next talk. Yes.
part.
Yeah.
Okay, thank you. So next I'm gonna introduce Dr. Subhankar Khatua. He passed out he did his BSc from RKMRC in 2013, and now he is doing his integrated PhD from IMSC Chennai in condensed matter physics. Recently he visited from Department of Physics and Astronomy, the University of Waterloo, from March to August. He will give his talk on the low energy effective theories of quantum spin clusters, geometric phases, and bound state formations by singularities. Subhankar da.
Yeah, am I audible and visible?
Yes, you can.
Yes.
Yeah. So thank you very much, Olivia, for this kind introduction. So by the way, I'm not a doctor yet, so before I begin my talk, I'd like to thank MP Sir and Olivia and other organizers for giving me this opportunity to speak here. It's really special to be able to speak at our college, even though virtually, at the special occasion of Diamond Jubilee celebration. So let me share my screen. And I think I have not shared my screen. 1 second. Is my screen shared?
Yes.
Okay. So last few days when I was preparing for these talks, I was making these slides. Like many sweet, weird, many random memories were coming up of my 3 years college life. But anyway, so today what I'm going to talk about, and then Abhishek, thank you for this nice, wonderful talk. So today what I'm going to talk about is effective theories of spin clusters, geometric phases, and order by singularity. Please don't worry if you don't understand some parts of the title. It will be clear in the course of the talk. So this work is done in collaboration with Dept from IISc and Ganesh, my supervisor from IMSc. So the part I'm going to present today is a part of the full work which has been published in 2019. This is the reference for that. If you want to learn more about this work, you can please look up to this reference, or you can anyway ask me any questions anytime if you have. So I'm right now I'm not looking at the chat box. So if there are any questions or any comments, please pass it to me. And maybe it would be, I don't know if it will be better or not. So on the way, if I get questions that might be better for the audience, I don't know. Let's see how it goes. So so in the title, as you have seen, this effective theory. So let's first understand what I mean by an effective theory. So an effective theory for a system at some interest of at some regime of interest. It's simply a simplified theoretical model which is sufficient to describe a system in the regime of our interest, typically low energy or high energy, or whatever it is, overlooking all complicated interactions present amongst the constituents of the system. So in simple terms, so say you have a system and then it has several microscopic constituents. They are interacting amongst each other via complicated interactions. Now suppose in some regime of interest, suppose we are interested to understand the features or the behaviors or the physics of the system. In that case, maybe we can just simply overlook all the complications present in the microscopic level, and we can simply give a model, theoretical model, which would explain the behavior of the physics at that regime. So then that would be the effective theory for the system at that regime. So that's how we define an effective theory. So let us take a couple of examples. So the first example I will be taking is the projectile motion of a ball. So here is the. So is my cursor visible? Hi.
Yes.
Okay. So here is a cartoon picture for the projectile motion for a ball. Suppose we are throwing the ball with a velocity u and at an angle theta with x-axis, and this is y-axis. The gravity is working along minus y-axis. So just to let's say we want to understand what is the position and velocity of this ball at a later time t, let's say, and you have released the ball at time t equals to 0. So just for answering these kind of questions, or to understand the motion of the ball, Newton's law is sufficient to understand it. So we don't need to know that the ball is made up of atoms, and which is further made up of electrons, protons, and so on, and they obey Schrödinger's equations. They have Coulomb repulsions and so on. We don't need to worry about those stuff. We can just simply start from Newton's law and then understand its motion. So it's like quote unquote, for this regime of interest, Newton's law is sufficient. Let's see the second example. Second example is paramagnet to ferromagnet transition. So what would be its effective theory? Let's consider the material to be crystalline material, where you have lattice structure, and then the effective theory would be given by magnetic moments. They would be sitting at lattice sites, and say they are interacting in the following manner. So their Hamiltonian is given by this, where Mi and Mj, they are the magnetic moments at site I and site J, and so this angular bracket Ij refers to the nearest neighbor interaction. Let's say here are my magnetic moments at each lattice sites. So only the nearest neighbor, they talk to each other. It's not that this one is talking to this one. It's not that. And this J is positive. That's how the entire coupling is ferromagnetic. So negative sign is sitting here. Now a cartoon picture for this phase transition here. So let's say when temperature, we have the temperature which is much larger than the phase transition temperature, which is Tc. Then the magnetic moments are orienting in a totally random directions. So the total magnetization of the system is on average 0. So it has been captured in this cartoon picture. This is total magnetization is 0, and then gradually if you decrease the temperature near the phase transition, what happens is it forms domains where in each domain the magnetic moments are pointing in different directions, and so around Tc still your magnetization is 0 or non-zero. It would be very small or something like that, and then when you finally less than Tc, all the moments are pointing in direction. So thus this Hamiltonian is enough to capture this physics. You don't need to start from the electrons. They are moving in the lattice, and they are interacting via Coulomb interactions, and then there are ions and so on. You don't need to worry about anything like that. So this is the effective theory for the regime of interest. Here for the phase transition. So let's say we have understood let's say we understood what an effective theory is. Now what is the goal? So let us discuss the goal of this talk. In this talk we want to find out the low energy effective theories of the following fully coupled spin clusters. So first of all, we would be discussing or finding effective theories. Now the regime of our interest is low energy. At low energy, how these systems behave, that we want to understand, and the systems we want to consider these following systems. So by spin clusters, what I mean, these are clusters of spins, like a small combination of spins. They are not large spin systems or magnets. They're just small clusters. And what I mean by this fully coupled, it's like in one cluster, each spin is talking to every other spins. So everybody is talking to everybody else in the system. So here I have given a picture of a dimer. So as you see, this dumbbell shape. So at this gray ball shape, these will call as vertices, and there the spins are sitting. So in dimer there are two spins, one here and another one here, and this straight line, gray straight line, that represents the bond between them or the coupling between them. So it's like two spins, they are interacting with each other. So this will call as a dimer. So and what the particulars of the coupling will be. So this is what we are calling as a trimer. So one here, another one here, another one here, and everybody is talking to everybody else. Suppose this one is interacting with this one via this bond, and this one is interacting with this bond via this bond, and similarly this one is also talking to these two, and so on. And these bond lengths, they are same for any two spins. That just represent that they have equal coupling between amongst them. So this is trimer, and finally the last cluster we will be considering, that is quadrumer or a tetrahedron, if you like. There we have four spins, one here and one here, and then rest two here, and each spin is talking to everybody else. Suppose this one is interacting with this one via this bond, and then there is this bond here and this bond here, and for this one also there are three bonds. So these are the clusters we would be considering, and we would be finding out their low energy effective theories. So these are the systems. So now the natural question arises, like why we are interested in these clusters? Why not other clusters, or even why we are interested in these clusters? So to answer that, these clusters are building blocks of the commonly occurring large magnets. So let us see. Suppose, as you can see, this is a square lattice magnet. So at each vertex there are spins sitting. And as you can see here, I have marked this is a dimer. So it's like dimer is the dimer, this one. Dimer is the building block of this entire square lattice magnet. And similarly for a triangular lattice, so here there is a triangle. So trimer is the building block for this large magnet. And probably you might not have seen this kind of a lattice. So this is what we call a pyrochlore. So essentially pyrochlore is a corner sharing tetrahedra. So suppose, as I have said, this is a tetrahedron. So let's say you have a tetrahedron here. Let's say this is a tetrahedron, and then from each vertex you have another tetrahedron coming out. So from this vertex there is this tetrahedron came out. From this one, this tetrahedron came out, and from this vertex also there will be another tetrahedron, and this one also there will be another tetrahedron, which I have not shown in the figure. But anyway, so from each vertex of the tetrahedron there will be another tetrahedron coming out, and again the other tetrahedron also. So similarly from this one also there will be corner sharing tetrahedron. So that's how it will form the lattice, and that lattice we'll call it as pyrochlore. And just for the information, the Bravais lattice, underlying Bravais lattice for this is FC. But anyway, so here also you see that tetrahedron is the unit cell. So knowing effect, so these are the commonly occurring magnets. So knowing the effective theories of the building blocks, effective theories of these clusters would help us find the effective theories for these large magnets. At least that's the hope. Now that's not the only thing. So you would see that cluster effective theories by themselves are very rich in physics. That we'll see in the course of the talk. And along with that, we'll see quantum particle dynamics on non-manifold space. By non-manifold, I just mean self-intersecting space or something like that. But we will see examples. And then role of geometric phases, and then order of singularities. Before we go into, so let me first state a general principle here about the effective theories of these clusters. So the principle is at low energy, so this is the regime of interest. At low energy, the physics of a spin cluster or any large spin system maps to that of a quantum particle moving on the corresponding classical ground state space. So let's forget about this, what is corresponding classical ground state space. For the time being, let's consider, let's just assume that this is some kind of space. And so the effective theory is given by the effective theory, low energy effective theory of the spin clusters is given by quantum particle dynamics on that space. Now you'll try to understand what that space is. So before we try to understand what is this classical ground state space for a given spin cluster, so let us recall a few basics of path integral quantum mechanics. I believe that most of the audience is undergrads. You might not have studied this path integral quantum mechanics or statistical mechanics, but even if you didn't, don't worry. This is just one slide, and we will move on to the next part soon. So in the path integral statistical mechanics or path integral quantum mechanics is generalization of Lagrange formulation in classical mechanics to its quantum counterpart. This is given by Feynman. And in classical mechanics, you know that there are only unique classical trajectories. But when it generalizes to quantum mechanics, it becomes the sum over all possible trajectories with proper weights. And now, for the following statements, I don't want to prove it here. I just urge you to assume the following statements to be true here. So at the low energies, the partition function. So I'm sure all of you have seen partition function in statistical mechanics, which is trace of exponential minus beta h, where beta is inverse temperature and h is Hamiltonian. So that also you can write it in the path integral formulation, and so there it would be simply sum over paths with some proper weights. So the paths will be having some weights, exponential weights. Now, so please believe me in this statement that the partition function is dominated at low energies. The partition function is dominated by the paths within the classical ground state space. Let's say you have some quantum problem. Now you are doing path integral for that. So what you would see that the partition function, so there will be more contribution to the partition function from the paths within the classical ground state space than the paths outside the space. So let's just believe that this is true, and then go ahead. We'll see what happens. So now let's see what a CGSS is. So CGSS is just abbreviation for a classical ground state space. So how do I? So here also I want you to believe this. So how do I achieve a classical ground state space for a spin system, quantum spin system? It can be achieved by minimizing the Hamiltonian. So whatever the Hamiltonian you have for quantum spin system, what I have not discussed so far, but for a given Hamiltonian, you can minimize that Hamiltonian considering the spin operators to be 3-component vectors of fixed length. So let's say you have some Hamiltonian, and then you replace those spin operators by a 3-component fixed length vectors, and whatever you get, whatever function you get, then you try to minimize that, and you'll be getting some space after minimizing it. That would be your corresponding classical ground state space for a given quantum spin cluster. Okay, so from this first statement, that partition function is dominated by paths within the classical ground state space, it is kind of intuitive that, if I go back to the last slide, intuitive that if in the low energy effective theory, somehow this classical ground state space has to arise. Okay, so let us recall the principle we had stated. So the low energy physics of the clusters map to that of a quantum particle moving on the CGSS. So all the examples we will be taking, there would be finding out what is the CGSS. Then we would be studying a quantum particle dynamics problem on that. Then we'll compare the spectrum for the given quantum problem and this equivalent particle problem. Then you would see that they agree really nicely. So that's how we will show that is the effective theory and so on. And the Berry phase term in the spin problem, that might result into threading of non-trivial magnetic fluxes through ground state space. So in the ground state space, the particle will be moving in the equivalent particle picture. It would see some magnetic fluxes if there is non-trivial Berry phase in the spin problem. But for this talk, actually, I won't go into the detail of this Berry phase and all. But let's see how far we can cover. I'll just touch upon this idea. So okay, so the clusters we have taken these dimer, trimer, and quadrumer or tetrahedron. And the Hamiltonian we would be considering here is this. Hamiltonian is this. Here, as you can see, the sum over I not equals to j. So it's like no spin is interacting with itself, but it's interacting with everybody else. So here we would be considering only xy dot products. So this dot product is, so it doesn't have any, it doesn't contain any j component, and j is antiferromagnetic, greater than 0 we consider. So this particular Hamiltonian we take here, maybe you can consider any other Hamiltonian of interest. But for this particular Hamiltonian, how the effective theories emerge and how interesting they are, that we'll see. So essentially, I'm sure you guys have understood this Hamiltonian. There is no confusion about this Hamiltonian, I guess. So let me clarify this. Let's say for this dimer, there is 2 spins, 1 and 2. So this Hamiltonian would be like simply j. There is no sum. Forget about this sum. S1x, S2x plus S1y, S2y. Simply that. And for trimer again, there will be like term for 1, 2, term for 2, 3, and then 3, 1. And then for quadrumer again, there will be similar terms. Now, as I said, for the sake of low energy effective theory, we have to first find out what is the corresponding classical ground state space. So, given this Hamiltonian, as I prescribed the way to that. So this is Hamiltonian. You can rewrite it in this form. Square, so this is sum over spin and then square, and minus sum over square of the spins. So for any particular systems with particular spins, so this is a constant kind of a term. So only this part you have to minimize. Now, since the dot products involved are xy dot products, to minimize the energy, this term, the spins must lie in the xy plane. So first of all, this is xy dot product. If they do not lie in xy plane, then the energy will be higher than what we had if they would lie in xy plane, and they have to add to 0, because so this is a total square and its minimum value would be 0. So sum of the spins have to go to 0. That would be our ground state condition, classical ground condition. So I hope this is clear to everybody. This is the basics of what I do further. So maybe I'll repeat this once more. So we have just rewritten the Hamiltonian, and then we are minimizing it. The minimizing criteria is all the spins in the system, they have to lie in xy plane. This is a bit of algebra, but this is very trivial. You can do it for yourself if you like. But they have to lie in xy plane, and they have to add up to 0. That's the criteria for the ground state. So that's the way we would find out classical ground state space. So, excuse me. So the first example in hand is XY dimer. So okay, the dimer had the dimer has 2 spins. So the ground state condition we have discussed already. So they have to lie in xy plane and they have to add up to 0. So which is 2 spins must lie in xy plane and align opposite to each other, because like if there are 2 spins S1 and S2, if they have to add up to 0, they have to align opposite to each other. Now, so which is something like this: 1 and 2, they are anti-aligning. So this is a ground state configuration. Now, so this is not the only ground state. So now let's say you rotate this entire thing by an angle phi. Still that would be in the xy plane, and as you have rotated the whole thing, then they would be adding up to 0 as well. So that would also be a valid ground state configuration. So what does that mean? So the space of all such ground states would be a circle, which would be parameterized by the single parameter phi, which can take value from 0 to 2 pi. So that's how we claim that, or we argue that the circle is the ground state space for the dimer. Circle lies on the xy plane. Now, so our Hamiltonian is very simple. S1 dot S2. I mean S1x S2x plus S1y S2y. So let's say we can write down, if it is for spin half, we know what is S1x S2x and S1y S2y. Then you just add them up. You can find out their quantum spectrum. So far what I was talking about the classical problem. For the time being, forget about the classical problem and let's focus on the quantum problem itself. Now, suppose we have this quantum Hamiltonian. Now we know their matrix forms. If it is spin half or if it is spin 1, whatever it is, we know their matrix forms. And then let's say we write down the Hamiltonian, and we find out their eigenvalues. Somehow we find out. So here what I have done is I have done something like that, but this I have done in computer. So I have used Mathematica. There I have written spins for. So I have written Hamiltonian for spin 8.5 or 9, for 9.5, 10, and then so then I have calculated the spectrum or the eigenvalues, and then I have plotted it here like this. So as you can see that the ground state is here. This is the ground state. So there are different markers for different spin values. You can, for the time being, you can focus on only one marker. Let's say the green one is visible. So let's take this one, spin 10. So here you see that the ground state is degenerate, which is lying at 0, and then first excited state is doubly degenerate, which is at 1. Then second excited state is again doubly degenerate, which is lying at 4, and so on, like 1, 0, 1, 4, 9, 16, 25. So it is going as n square, where n is integers. So ground state is non-degenerate, and excited states are all doubly degenerate. So and this is what I have done is I have first of all shifted the spectrum by the ground state energy. So by doing that, actually I don't change any physics, and then I scale it by delta. This delta is actually the separation between. So please do not worry about this delta. So this delta is the separation between first excited state and ground state. So anyway, so this is my quantum spectrum, and this is my classical ground state space. So circle is my classical ground state space. This is my quantum spectrum. Now I don't know if this looks very familiar to you. So let us go to the next slide. So let us recap the quantum mechanics of a particle on a circle. So the Schrödinger's equation for particle on a circle is this, and the wave functions given by exponential I n theta, where n takes value 0, plus minus 1, plus minus 2, and so on. Eigenvalues be given by this, where if you just assume h squared by 2m to be 1, then it is just n square. Then so the eigenvalues are 0, 1, 4, so on. Here you see that. So, and here also you see that the ground state is non-degenerate, and excited states are all doubly degenerate, because n being plus 1 or minus 1, they have the same energy, n square. Thus you can see, if you like, I have not plotted this, but if I plot it, it will be exactly this. Ground state is degenerate, and excited states are all doubly degenerate. So this delta, what I was trying to avoid, or was not trying to explain, this delta has a relation with the mass of the particle. So essentially this is my, so there is no classical assumption here. This is totally quantum. I have just solved the quantum spectrum, and I have separately found out what is the CGSS, corresponding CGSS, and then I have studied the quantum particle dynamics on that CGSS. Then I see that they are exactly the same, but they are not same, everywhere else. So only at this part they are same, as you see. So that's why the low energy physics. So the low energy physics of the spin clusters is same as the particle moving on the corresponding classical ground state space. So I'm not sure if this is understandable to everybody, but so this is what it is. So given a spin problem, we solved the spectrum from quantum mechanics, and then we get the classical ground state space. We solve the particle dynamics, quantum particle dynamics on that space. Then we show that at low energy they agree. That's what we have shown for Diamond. Now let's go ahead to discuss the trimer case. So for trimer, we have 3 spins. Again, the ground state configuration would be given by 3 spins lying in the xy plane, and they add up to 0. So how we can achieve that? Simply by configuration where so something like this, where each spin is making 120-degree angle with everybody else. Suppose the spin 1 is making 120-degree angle with spin 3, and 3 is making, and 1 is making 120-degree angle with 2 also. So like all these angles are 120 degree. So this is the way we can add 3 planar vectors to 0. Now again, similar to dimer, so this is not the only configuration. Let's say 1, 3, 2. This is not the only configuration. What we can do, we can rotate this in xy plane rigidly as in, so this 1 intact xy plane, still that would be a ground configuration, still they are 0. So thus the circle will be a ground state space. Is single circle is the ground state space, or there is something more? So let's see. So you let's say we have this 1, 3, 2, and then we rotate it and we got a circle. Let's say we have something like this: 1, 2 here and 3 here. and as you see that they are classically distinct configurations, and you can rotate this one, and similarly you will be getting a circle here also. But now there might be questions, are these two circles, so now these two circles are the ground state space, and now the question would be, are these two circles disjoint, or they intersect? So as you can see that from any point on this circle, you cannot go to any point on this circle without leaving the plane. So the ground state configuration, the criteria for that was you have to be always on xy plane. Suppose if you want to go from here to there, then you have to leave the xy plane, because see, if you have to just split 2 and 3, for that you have to continuously deform it, but it won't be then in xy plane. So the two circles are my ground state space, but they are disjoint. So what I have shown here. So for this problem also we have found out what is the ground state space, which is two disjoint circles, and then again we can similarly study the quantum particle dynamics on these two disjoint circles. We then compare that with the quantum spectrum. So in the similar fashion as dimer, we find out the quantum spectrum for primer also for several spin values. Then what we see that the ground state here again 0, 1, 4, 9, 16, 25 and so on, what has to be there for particle on a ring problem or circle problem. But here the ground state is doubly degenerate, and then every other excited states, they are all fourfold degenerate. But in the particle on a ring problem, what we saw, the ground state is non-degenerate, and then every other excited states are doubly degenerate. But like what happened here then? So actually it's essentially because of these two circles. Because of two circles, the degeneracy has doubled. Every state has twice the degeneracy. That's why the ground state is double, excited state is fourfold instead of two. So again, the agreement is really nice. So here, as you can see, I have given the data for only integer spins. Like why I have not given data for half integer spins? So if we again find the quantum spectrum for half integer spins, I'm still audible, right?
Yeah, you are.
Oh, okay. So thank you. For half integer spins, as you can see that I don't know if you can see this, that ground state space. So the ground states are happening at 1, and then 9, 25, 49, and so on. And the ground state is fourfold degenerate, and every other states are also fourfold degenerate. So, but in the previous case, what we have seen is ground state is doubly degenerate, and all other states are fourfold degenerate. But here, ground state itself is fourfold degenerate, and that is not also happening at 0. What we have seen here, the ground state here was happening at 0, but this is not happening at 0, like 1, 9, 25, 49, and so on. So the spectrum for half integer spins is not same as that of the integer spin case. So therefore, the question can come, at low energy, is it not a particle on two disjoint rings? Now the answer will be given by for half integer spins, the mapping is not just to a particle on two disjoint circles, it's to a particle on two rings threaded with pi flux. So there has to be a magnetic flux threaded to the ground state space. Actually, its origin in the spin problem is this Berry phase thing. So and I won't go deep into it, deep into this Berry phase thing, but that is essentially related to the non-trivial paths possible on your classical ground state space. But let us forget that for the moment. So here the take-home message would be, so for the spin half case, even though we don't have agreement with the particle on a corresponding classical ground state space, the correct mapping, low energy mapping, would be a particle moving on the two circles with a particular magnetic flux threaded through the ground state space. Essentially, if you this particular problem, we need to have pi flux threaded through the circles. So now, if you solve a particle on a ring problem with corresponding flux, this exact spectrum plotted here. So essentially, for this problem, the n is given by n minus 1 plus 2. And from there, you would see that every state is two-fold degenerate, and because of two circles, you would be having two more degeneracy. That's how it would be all four-fold degenerate states. So, so as you have seen in the title of my talk, that geometric phases. So this is the geometric phases I was talking about. So the very phase in the spin problem, that non-trivially manifests this magnetic flux threaded through the ground state space in the particle picture, equivalent low energy particle picture. Now, so I have covered already two cases. The final case, and which is the most interesting case, is this XY quadrumar, or the tetrahedron, the last problem we discussed. So, so again, like the other clusters, here also you have to find out what is the corresponding classical ground state space. So again, the same condition, that all the spins, they have to lie in XY plane, and they have to add up to 0. So here we have 4 spins, 4 same length spins. Now, for same length spins, same length vectors, to be precise, to be more correct, for same length vectors in the XY plane add up to 0, so that we can achieve here. So if they form a rhombus. So let's say, so by rhombus what I mean is that, let's say 1 and 2, they are anti-aligning, and 3 and 4, they are anti-aligning. So that's how they can add up to 0, and they all lie in the XY plane. So this is a valid ground state configuration for XY quadrumar. Now you can see, so here, so again, 1 and 2, they are opposite to each other, 3 and 4, they are opposite to each other. But then you can see this direction of spin 1, which is given by this theta 1, it can be anything from 0 to 2 pi. And then accordingly 2 will anti-align to 1, and similarly this 3 can point in any direction with respect to this direction of spin 1. That also can be anything from 0 to 2 pi. Still it would be a valid ground state configuration. So thus the entire ground state space would be described by these two angular parameters, theta 1 and say here theta 3 1. So, and these thetas would be taking values from 0 to 2 pi. So thus it would be like direct product of two circles. So there are two thetas involved, and they are totally independent to each other. That's why the ground state space would be a direct product of two circles, which is a torus. So torus, as you know, in torus there are two angles involved. So I don't know. So let me just show it here. Am I visible? I'm visible, right? Hi.
Yeah, I can.
Yeah, we
can see
can.
me, okay. So you can see a piece of paper in my hand.
Yes, I can see.
Oh yeah. So essentially, this is a piece of paper. I have rolled it, and so a torus we can form by bending it and connecting it here. So there are two angles involved, as you can see. This is a very bad torus, but still you have to bear with me. So this angle is one angle, and then this another angle, which is this one. There are these two angles involved. So thus the ground state space for XY quadrumar is a torus. Now, is it a single torus, or there is something more to it? So here we have assumed that 1 and 2 they are always antiparallel, and 3 and 4 they are always antiparallel. So okay, before going into that, let me just explain this torus here. So let us consider this one. this figure. So here theta 1 goes in this direction and theta 3 1 goes in this direction. Now so if I specify theta 1, any value of theta 1 and any value of theta 3 1, that would be specifying a point on this whole space, and like one point on this space. If you tell me one point on this space, I know like what is which direction 1 is pointing, and then accordingly 2 would be anti-aligning, and then from theta 3 1 I know which direction 3 would be pointing, and similarly 4. So a point on this space would be giving me a ground state configuration. So this is my ground state configuration, what I have described so far. And this theta 1, once it comes to 2 pi, it is same as this point. This point is same as this point, and similarly for like any point on this side is same as any point on this side. And similarly any point here is same as point here, because they have to again wrap up when it goes to 2 pi. So that's how it is a torus. So far I think it's all clear. So and on this space it is always that 1 and 2 anti-aligning, 3 and 4 they are anti-aligning. So now here we have taken that 1, 2 anti-aligning always, but so what we can do is that we can take 1, 3 to be anti-aligning and 2, 4 to be like this. That will also give me a torus, which is essentially this. And so the last torus, this one we can obtain by making 1, 4 to be anti-aligning and 2, 3 to be anti-aligning. So there are there's 3 tori. Now so it might seem that these 3 tori, they are all disjoint. So the ground state space is a combination of 3 disjoint tori, but this is not the case. Here these 3 tori, they are intersecting with each other. So let's see how. So first of all, there are total 3 tori for the ground space of Equadoma. And now let's see if there are any common lines or common regions between 2 tori. So let's see. So let's just consider this black line. So this black line refers to this kind of a configuration. So 1, 2 anti-aligning and 3, 4 anti-aligning, but this relative angle here, theta 3 1 is 0. So this one is 0. So that's why they are always they are always in the same direction. But as you vary theta 1, so this entire rod would be rotating in xy plane. So that represents this black line. But now let's go to these torus, and let's come here. So here theta 2 1 is pi. So if theta 2 1 is pi, this angle is pi. So by that, what will happen is like 1, 4 will be anti-aligning, and 2 will be again. So essentially we'll be getting this configuration. So if you look at this carefully, then on these torus also we'll be getting the same black line here. So by same black line, what I just mean that even though we are saying there are 3 tori, they are not really disjoint. There are common lines. So there are same configurations on these torus and on these torus as well. So they cannot be disjoint. They are connected. So this black line is common here. Similarly, this red line is common between this one, and this green line is common between this one and this one. So as you can see, and then these, so as you can see, let's say black line is repeated here. That is just trivial because the 2 pi and 0, they are the same lines. So anyway, so between these 2 tori, you see that red line is common. Between these 2, there are again this green line common, and between these 2 also there is one common line, which is black. So between every 2 tori, there is a common line. So this is our cartoon picture for the classical ground state space. So this is a cross section shown here. So it's like, so there is a big torus, something like this. So here it is, here now this way it is going into the screen, and this way it is coming out. That's how the torus is. and two more tori, they are sitting inside the big torus, which are this. It is going inside the screen and coming out here, and another torus, which is this one, is going inside the screen and then coming out this way. So here, please do not worry about the radius of the tori and so on. Here I have just tried to capture the connectivity of the space. So as you can see, between this torus and this torus, so you see this red dot. So this is not a red dot. This is the common line between this torus and this bigger torus, which goes into the screen here and comes out here. So this is like a line goes through the space, and it's between two tori. And this similarly, this green line going into here and coming out here, which is the common line between the yellow and this pink color tori, and similarly the black line also between this one and this torus. So essentially, so space is so far the ground state space we have seen single circle or two distant circles. They are all non-intersecting or smooth manifolds. But here we can see that the ground state space is a self-intersecting space of three tori, intersecting tori, two tori. They are intersecting along a line, common line. So the space is non-manifold here. The non-manifold in this sense that you cannot, and the space is not smooth there. Once you go there, you don't have the notion of differentiation there, spatial differentiation. I'm saying. So I hope this ground state space idea is clear, because this is very crucial. If not, I'm happy to answer any questions, doubts, comments. Welcome. Maybe I'll go ahead and let's see. So far what you have seen, that so far we dealt with smooth spaces. Before quadrumor came, we have dealt with smooth ground state spaces. But now the space is a self-intersecting space. It is a non-manifold space. So how do we solve the Schrodinger's equation? So always we solve the Schrodinger's equation by considering double derivative in space and single derivative in time. But here the space is intersecting. So then what do you do? How do you solve Schrodinger's equation? But still the claim is valid. The mapping to a particle moving on the corresponding classical space, that is valid. That I would show. So then in that case, now I have to somehow find out the particle dynamics, solution of particle dynamics on this kind of a self-intersecting space. So in order to find out the solution for this particle dynamics on this space, what we do, we follow this procedure. So we discretize the space keeping the same connectivity. So whatever the space we had, three tori space, we keep the space and we discretize the space, but we keep the same connectivity and study a tight binding problem on this. So tight binding problem as in like we keep a particle and then that hops from one side to another, and so on. And we solve that problem. We write down the Hamiltonian for that problem, and then we solve it and we get the spectrum. And as we increase the discretization, as in give more and more points to the space, it mimics more and more to the actual particle dynamics problem on this space. So before we go to the actual problem, so let us get a flavor of this kind of discretization on a figure of 8 space. So let's say this is a figure of 8. Let's say we had a smooth space and then we discretized it like this, and then we are studying a particle problem on this particle dynamics problem on this space. So as you can see that even though you have discretized, so on figure of 8, how do we write such that Hamiltonian for the particle going from here to here. So Hamiltonian and here present the ground state configuration. for this problem. For this figure of 8 particle dynamics problem, I have just given the ground state configuration here. So here the heights, what it measures is the probability for the ground state configuration. So the quantum ground state we find, and this is the probability for the wave function. Then you see that at the ground state, the particle is the probability for finding the particle is really high here and almost zero everywhere else. So at the ground state, the particle likes to get bound here. The ground state is really localized at. Okay, so this is the flavor of singularity or non-manifold to a quantum particle. So you had a space something like this, and then you are studying a free particle motion on this space, and you see that ground state configuration is such that the particle is bound here. But anyway, so this is I'm not exactly describing how the space is discretized, but there are ways to discretize this space, and we discretize it. Okay, so before we go into that, so this is again here also is non-trivial Berry phases, and then there will be a flux problem. So this pi flux threading will also be there, but let's not go into this. So I have for the quadrumer problem, I have discussed at the ground state space. I have discussed how to solve the particle dynamics problem, as I didn't know how to analytical Schrödinger's equation. I didn't know how to solve it. Non-manifoldness, described a way to find the particle dynamics in this space, and then let's say I know how to solve the quantum mechanical spectrum also. Then if I compare, then you see that okay, let's first see this plot here. What I have plotted. So these these blue markers, the blue diamond markers, they are for the tight binding or the particle so particle moving on this discretized space, and square markers are for the actual quantum problem spectrum for s equals to 4. So and L equals to 12, what does it mean that? So you had let's say in one torus you have 12 by 12 sides. That's the way we have discretized it. And then there are the 3 tori and so on. So and then you see that there is a very nice agreement between the tight binding model and the actual quantum spin spectrum. And similarly, if you just increase spin, let's say here I have shown it for spin 12, then also you see that for L equals to 22, there's a very nice agreement between the particle dynamic spectrum and the actual quantum spectrum. And here I have given 2 panels for half integer spins, but again half integer spins, they differ from integer spins, and as I have said, there is non-trivial Berry phase, and that explains that, and that's why this nice agreements again. But anyway, so far I have been telling that so far I have been telling that so far I have been telling that we can obtain this Hamiltonian spectrum by writing down the Hamiltonian by writing down the spin matrices, and we can construct the Hamiltonian, then we can diagonalize it and so on. But this is not always a very easy task. So let's see how. So let's see how we do it. So how we numerically actually do it. So there are computer packages which diagonalize a Hamiltonian matrix. So so what you have to do, the main task is to input the matrix in a desired format, and then the computer by itself will do the diagonalization, and it will spit out the eigenvalues and eigenvectors. Thus, the calculation of the matrix elements has to be known beforehand, because that's what we have to input in the machine. So it's not very difficult always to calculate this matrix element. This part might also be easy to do, calculating matrix element, because given Hamiltonian, the basis, you can calculate the matrix element. So what is difficult? The main issue is the size of the matrix. The maximum size of the Hamiltonian matrix, which can be diagonalized in computer, is roughly 10,000 by 10,000. So you have this entire Hilbert space. So you have to see so if you have a space, which is 10,000 by 10,000, so 10,000, let's say, then easily you can do it in computer. But let's say, for your interest, you want to exceed this number, you want to go beyond this number, then what you would do? Okay, let me first give a rough estimate. So Hilbert space size, so in computer what you can solve is this 10,000 by 10,000. Let's say, so Hilbert space size of a spin S quadrumer is 2s plus 1 whole to the power 4, because for each spin 2s plus 1 dimension, and then for quadrumer I have 4 spins. That's how 2s plus 1 whole to the power 4 dimensional Hilbert space. Thus 2s plus so 2s plus 1 2s to see S max is 9 over 2, 4.5. But as you can see here, I have solved the spectrum for S12, or even, okay, so anyway, I have gone up till S12, and in this talk itself I would be saying that we have gone till S19 as well. So then how do we do it? So in most cases, so the next bullet is, in most cases we need to go much beyond this size, and how much, that depends on problem in hand and interest, and how to then access larger Hilbert space computationally. This is answered by this. So the use of the symmetries is the key. So symmetries of the Hamiltonian that further break the Hamiltonian matrix, or the large matrix, into several block diagonalized matrices, and we can separately diagonalize these blocks in the computer. So in that way we can access huge Hilbert space using the symmetries. Now note that the computational spectrum, what I have been showing, that is exact. There is no approximations involved. So what you would be doing in pen and paper, with pen and paper, that we are doing in a computer. There is no approximations involved. The spectrum is totally exact. This is a cartoon picture given an n by n matrix. Using the symmetries, you can block diagonalize the matrices further, and and then separately these blocks you can input in the computer and find out the spectrum. That's how you can access these larger matrices. So recall the spin angular momentum addition. Say you have Hamiltonian equals to S1 dot S2. Let's say you have just two spins, S1 dot S2. H is 2s plus 1 whole square equals to 4 by 4 matrix for a spin half problem. When you have S1 and S2 to be half, then your Hilbert space size is 4 by, Hilbert space size is just 4, so the Hamiltonian matrix would be 4 by 4. Now you can define something called S total, which is S1 plus S2, and then you can show that S total I and H, so I stands for X or Y or Z, they commute. So which means that total spin, this S1 plus S2, that is a symmetry as it commutes with the Hamiltonian. Thus Hamiltonian breaks into two blocks with S total equals to 0 and 1, corresponding to singlet and triplet states. As we know that singlet and triplet states, everybody knows, I guess. So the 4 by 4 block, 4 by 4 matrix breaks into two blocks. One is 3 by 3, another one is of size 1 by 1. This is an example for how we can use symmetry and do this. So the symmetry classifications and everything we have to do before, and then finally these block matrices we have to input in computer and get the spectrum, and that's how we I have found all these spectrums. So just last 2-3 slides left. So here exact diagonalization. So the numerically I have, so this is the spectrum of the quantum problem for spin equals to 19. So spin 19, so what would be the Hilbert space size? So it's like 2 into 19 plus 1 whole to the power 4. So it's really huge. So for that we had to use 3-4 symmetries and so on. But anyway, so the so if you see this spectrum, you see that there is something really interesting here. So again, you see that 0, 1, 4, 9, 16, 25, and so on. But this ground state is 3-fold degenerate, excited state is, and all other excited states are 6-fold degenerate. So it really maps to a particle on 3 disjoint circles. So if you have particle on a circle, then ground state is non-degenerate, and then every other states are doubly degenerate. But so if we just triple the number of circles, let's say you have 3 degenerate circles, in that case all the degeneracies will be tripled, and that's how you'll be obtaining this 3, 6, 6, 6, 6, and so on. And the numbers also, you see that they match nicely. So essentially, so initially we have shown that a quantum spectrum matches with particle moving on the corresponding CGSs. But again, further it boils down to particle moving on 3 disjoint circles. It's not so now anymore. No more it's a particle on entire ground state space or entire this intersecting 3 tori combination. It's just particle moving on 3 circles. So this is what we see for very large spin 19. So what is really then happening? So this behavior actually you have not seen for a dimer case or trimer case. That it's just particle on the CGSs. Here for smaller spin values, particle on CGSs, but as we increase spin values, it's behaving differently. So what's really happening? So this is my almost last slide. So what's really happening is that so those 3 disjoint circles what we were mentioning, those are really these line of singularities. So the line of singularities here are the circles, as I have already mentioned. So this black circle or the green circle or the red circle. So there are 3 circles. It's like the low-lying states, they are the particle, rather than particle moving on the entire ground state space, they are moving on these lines, singular lines. So here so on this plot, what I have presented here is the ground state configuration of a particle moving on this kind of space. So ground state configuration on one torus. So this is a torus. First of all, there are another 2 tori, which I have not shown, but they are similar to this plot. But on this torus, what I have presented is the ground state configuration of a particle moving on this entire space. But if we do that, so what we see is that, so as you see these red circles with bigger circles, bigger red dots are here or here. They are not in between. So the size of these circles at each point is proportional to the probability of finding the particle at that point. So then the probability of finding the particle is more here or here. It's very negligible at the rest part of the torus. Thus, so this is what we have shown for ground state, but many low-lying states are so essentially. Then what we would say that at very low energy, the particle, even though we are releasing the free particle on this whole space, it likes to get bound near these singularities, singular lines. So here the probability is more, here the probability is more. At the ground state, like it's getting localized near the singularities. What we have seen in the figure of 8 case. And many states are like this. So the effective theory then for this case is a particle on 3 disjoint rings, which are the singular regions, and this is what we call as order by singularity. It's like your classical ground state space is singular. It has self-intersecting regions, and these self-intersecting regions are making your free particle to get bound to them. So thus the singularity determines the low energy physics. Thus we call the physics as order by singularity, and which happens only at this problem, not earlier problems, dimer or trimer. There we haven't seen this kind of feature. Here we see this. So this is my summary of the talk. So free particle moving on the CGSs describes the low energy physics of the spin clusters. If the CGS is self-intersecting in nature, the low-lying states are bound states at the vicinity of the singular region, and the Berry phase part, which I have not discussed in detail in spin problem, manifests as the magnetic flux through the CGSs. So the particle will see a flux. Thank you. Thank you for your attention.
Thank you, Subhankar.
Yeah.
Are there any questions?
Yeah, please.
There is no questions yet in the comment box.
I see. Okay.
Hello.
It seems that everybody has understood it properly, very clearly.
Yes,
Yeah, yeah.
Hello, Subhankar.
Hi. Yes, yes. Hi. Hi.
Probably MP side.
Hello.
Hi, hi. Am I audible? I can hear you.
Hello, MP side, we can hear you.
Yes, we can hear you, sir.
Hello.
Hi, hi, hi. I can hear you. I can hear you. Hi.
Hello,
Hi,
Subhankar.
hi. I can hear you. Hi.
শুনে যাচ্ছেন?
আমি শুনতে পাচ্ছি কিন্তু
হেডফোনের প্রবলেম মনে হয়।
হাই হাই আমি শুনতে পাচ্ছি। হ্যালো হ্যালো
হ্যালো।
হাই। হেডফোন ছাড়াই কথা বলতে পারেন হয়তো।
স্যার হেডফোন ছাড়া বলুন অথবা টাইপ করুন, আমি বলে দিচ্ছি।
Oh, okay. Just left the meeting.
So there is another question from Shatanik.
Yes. Yeah, yes, yeah. Oh, sir has joined again, I guess.
Hello.
Hi, hi. Hi, I can hear
Subhankar?
you.
Oh, okay.
Yes, yeah.
Please go to the slide, quantum mechanics of a particle on a circle. Please
Yes,
go to the slide.
One second. Yeah, this one.
So this one. Right.
Yeah.
So eigenvalues En is directly proportional to n square, but n equal to 0. How is it possible? N equal to 0? Because particle is on a circle. So n equal to 0, that means En 0. So how is it possible?
What is 0?
N equal to 0. You have written
So
the n equal to 0, plus minus 1, plus minus 2, and so on.
Yes.
But n equal to 0, is it possible?
If you're,
how is it possible?
If your n equals to 0, then your wave function is just constant. Let's say 1.
Right, 0. Right, but energy is 0. Energy is 0. So how is it possible? Particle on a circle, right?
Yes.
So it has a constant energy there. Right? The particles always have a constant energy since the particle on a circle.
So it might be 0 as well.
But particle.
Why do you say it's not 0?
Because particle on a circle.
Yeah.
There is certain energy, right?
No, I'm just saying that it can be 0 as well. That's my point.
Okay.
So anyway, so if we just solve this problem, we see that these are the things.
Yeah.
So yeah, maybe from physics point of view, there might be question that how can the energy be 0 and all. I am not sure how to best describe this, but this is how it is.
Okay.
Yeah.
Very nice talk. Okay.
Thank you.
There is no questions in the YouTube chat box, so MP sir, vote of thanks.
Okay. Thank you, all of you.
So how was the talk overall? So okay.
All of you, any questions from audience?
No, sir, no questions from audience.
Yeah. Okay. So last is vote of thanks, right?
Yes, sir.
So good. Okay. So, good afternoon. On behalf of our Department of Physics, Ramakrishna Mission College, Narendrapur, I would like to thank the speakers, Dr. Abhishek Samanta and Mr. Subhankar Khatua. The students who are joining, also the thanks to the students who are joining this webinar. I thanks to the speaker, Mr. Subhankar Khatua. I hope that his valuable idea on quantum spin clusters and also the bound state formation by singularities always boost up our students to these studies. I also thanks Dr. Abhishek Samanta, who is talking on the superconductivity and its localization. I hope also that the students has gained the idea on this subject. Finally, I also thanks to my dear students, basically Oliprio and the Satanik. And again, I thanks to all. প্রত্যেকে ভালো থাকো, সুস্থ থাকো, এটাই আমি কামনা করি। অভিষেক, শুভঙ্কর, অভিষেক অনেক দূরে, শুভঙ্কর তবু কাছেই, আমার কলকাতাতেই রয়েছে। তোমরা সকলেই ভালো থাকো। আমরা তো আর এসব এত কঠিন কঠিন জিনিস কিছু বুঝি না, সব ডিটাচ হয়ে গেছি। যাই হোক, খুবই ভালো লাগলো অনেকদিন পরে তোমাদের সাথে কথা বলে। ঠিক আছে, সুস্থ থাকো, এই আর কি। হ্যাঁ, অবশ্যই।
আর এটা সত্যি ভালো লাগলো এই ধরনের
হ্যাঁ, মানে না, এটা খুব তাড়াতাড়ির মধ্যে হলো তো। আর তাছাড়া আমি একটু ব্যস্ত আছি ন্যাক নিয়ে, সেটাও খুব চাপের মধ্যেই আছি। সোমবার সব জমা দিতে হবে, সেই জন্য খুব একটা মানে ভালোভাবে অর্গানাইজ করা গেল না। হ্যাঁ, অন্য টিচাররাও খুব একটা জয়েন করতে পারলো না, কাজ রয়েছে অনেকের এই ন্যাক সংক্রান্ত নিয়ে। যাই হোক, ভালো থেকো। হ্যাঁ, সকলে। অলিপ্রিয় শতানিক
বেরিয়ে গেছে, নেটে প্রবলেম হচ্ছে।
ও, শতানিক, আচ্ছা, ঠিক আছে। সব ভালো থেকো সকলেই। হ্যাঁ, ঠাকুরের কাছে কামনা করি তোমরা আরো বড় হও, আরো অনেক দূর এগিয়ে যাও, এটা আমি আশা করি। এটা তো সবসময় আমি চাই।